So let's begin the chapter 5.1 by looking at scalar and vector fields. This is going to be a refresher because I realize that I have already talked about these concepts, but it is convenient to talk about it again, to refresh it, and to introduce the notation that I will typically use during this chapter. Okay? So let's start with the concept of a scalar field. So our scalar field in physics applications is simply a scalar, which I typically write as capital phi, which depends on position. It depends on x, y, and z. Okay? Sometimes we just write this is a scalar phi, which depends on the position vector r. Okay? This is a scalar field. You can think about it as a function because it's a black box, which is our function phi, which has three inputs, which is the position, x, y, and z, and it has one single scalar output, which is phi. Okay? For example, one example of a scalar field would be the temperature of each point in a room. So, e.g., temperature throughout a room. Okay, so imagine we have a room defined in 3D with x, y, z. So the room is some sort of cuboid. And at each position within the room, for each position vector, we can define a temperature, T of x, y, z. And the temperature is a scalar quantity, right? So therefore, this is a scalar field. Other examples might be the pressure in a room, or in space in general. And another example could be the gravitational potential, which is also a scalar. So these are all examples of scalar fields. Next, we can talk about vector fields. So vector fields, they are a vector which depends on position. So this I typically write as capital F vector, never forget the arrow or underline it if you use that notation, which depends on x, y, z. Or sometimes you can write it as F, which depends on the r position vector. And the way you can see this is as a function that has three inputs, x, y, and z. And this function F produces three outputs, which are the three components of the vector F. Okay? Alternatively, you can write this as a vector R coming into the function and producing a vector F. Okay? In this chapter, I will always be using rectangular bases for the vectors. Let's see examples of this. So an example, let me copy the same graph as I had here. So an example of this could be the velocity of air in a room. For example, you have this room here, and at each point, the air is flowing, and it's flowing with a certain speed and with a certain direction. And this might be changing, right? So maybe there's a current coming from a window over here, and there is like a whirlwind, and things like that, right? So at each point, there is a velocity which depends on position. And since the velocity is a vector, this is a vector field. Okay? It's a vector that depends on position. Another example, less easy to visualize, would be the electric field. The electric field is an example of a vector field. Yeah. And another example would be the gravitational field. So you can imagine the gravitational field if the Earth is here or any other mass, m. So at every point, you have a gravitational field, which is a vector, which points towards the mass, right? And it gets weaker when you are further away. So this means that there is a vector which is a function of position. So that's an example of a vector field. Okay? So I hope those two concepts are clear. For visualization of fields, it's actually really easy to visualize these fields in 2 dimensions. It's not so easy to visualize them in a paper in 3 dimensions, but for 2 dimensions it's relatively easy. So for example, here on the left, I'm visualizing a scalar field given by phi, which is a scalar, which depends on x and y. So the way you do it is you plot your xy axis, and then for every point which has a value of x and a value of y, you can substitute x and y here, and you find some number. And that number you can codify it into a color by using a color bar. So let's say that this number is going between 0 and 1. So you just plot the color corresponding to that number at that point. And you repeat that for every point in the xy plane. And when you do that, you get something like this color map. This is called a color map. Okay? And you can even define these lines, which are lines of constant value of the scalar field. Okay? And this is very common, for example, in topographical maps, where you are plotting the height of the geography of some region as a function of x and y. Yeah? So this is an examples of scalar fields. Here, on the other hand, is an example of plotting a vector field. So this is a vector f, which is a function of x and y, but which is also a vector, right? Because you have x hat and y hat. So you have 2 components, the fx and the fy component. So this means that for every position in x and y, you can find a value for x and a value for y. You can substitute those into the appearances of the coordinates x and y, and you will get some vector. So you will get some number times x hat plus some number times y hat, and that vector you can now plot with the starting point at the location that you used to calculate the vector. Okay? So that means that every location is associated with a vector, which you can then plot. Okay? So this is the typical plot of a vector field in 2 dimensions. So I hope this is all clear. Now we are going to start working with these vectors and doing some operations to them. So see you in the next video.